All right, thank you, Daniel. And I think you can hear me as well, so let's get going. Hi, everybody. You may remember me from the first half. I'm aside from sending emails and organizing, I also have been leading the WMAP reanalysis effort within the Commander framework. And so I'll be giving a talk sort of on the sort of in media res of what's going on with this. So as a brief overview, this is WMAP. It observed from roughly August 2001 to October 2010, and had 9 years, 5 frequency bands, and it's a in some ways it's still a very useful data set because when you just think about where Planck LFI lies, the frequency bands lie right in between all the Planck bands. So that plus the fact that the 23 gigahertz map has a pretty good signal to noise means it's actually still a quite relevant data set, even if we have a perfect Planck data set. One other thing, other than sort of the final products, is that Planck's scan strategy is orthogonal to WMAPs. And we talked about the gain uncertainty modes in Planck, and also the poorly measured modes in WMAP, and a joint analysis with these experiments could, in principle, break the degeneracies between these two experiments' scan strategies. One other thing that makes a reanalysis of WMAP attractive is that the TOD processing is basically documented in the Lambda explanatory supplement. So basically, all you have to do is follow the explanatory supplement. So this is, again, very attractive. We decided to start with the WMAP K-band. It's sort of natural because, I mean, for one thing, the 23 gigahertz map is one of the best publicly available templates of polarized synchrotron. So understanding that will really be helpful for the future of CB polarization science. I already mentioned the explanatory supplement, which is an excellent document. And one what we might call bug that is actually a feature is that of all the WMAP bands, K-band has the largest side lobe contamination. And so this is a known effect that we will sort of need to do correctly. And once we do this, it will probably not be much more effort to do all the rest of the WMAP channels at the same time. And then finally, of course, the WMAP data are pretty low data volume. For example, the K-band data, uncompressed, uncalibrated, is about 100 gigabytes. And that's something that can be held in memory all at once on a relatively small computer, which was not the case during the WMAP science team's original analysis. In fact, their analysis method was to analyze the data 1 year at a time to see that the results were consistent over the years, and then took a weighted average of each of the final maps. So this is all to say, if we today just reran the WMAP pipeline from start to finish with the full data set, we would get a statistically more optimal solution for the WMAP data. So basically there's money on the table, so to speak. This is worth doing, even if there's nothing to be improved. So that's sort of motivating why we're starting here. So as a brief review, the WMAP is a little bit different from Planck in that it's a differential radiometer. You have two horns, A and B, that are observing two patches of the sky at the same time. And so it observes one patch of the sky, the other patch, and subtracts the two signals. So you end up getting an inherently differential signal. And then one thing that's very good about the WMAP scan strategy is that it orbits around its axis about every 2 minutes, and there's also a 3-month precession. So you end up covering most of the sky in a single day, and you cover the entire sky over every 6-month period. So one of the nice things about this is you reobserve the same pixel at different orientations many times, And that gives you really good control for systematic projection. So when we're actually talking about analyzing the WMAP TOD, it's worthwhile to actually look at what the data model is. So for the K-band, the data are split up into these differencing assemblies, which consist of 4 radiometers. You basically have the 2 orthogonal polarizations, and then there's also the difference time streams A minus B and essentially B minus A. So you have 4 NTOD data sets that you need to analyze. You also have the gain, which is the case for all CMB experiments. There's a baseline. And then there's this interesting factor, the beam transmission coefficients, alpha A and alpha B, which are essentially the efficiency for which radiation travels down the horn. And the fact that it could be different between each of the horns causes some interesting issues, which we'll get to a little bit later. Now, one thing that we had to do that was essentially the only new piece of code that had to be written in Commander 3 was the map making procedure. So as a brief review, this is a sort of cartoon of the pointing matrix and the map making procedure that needs to be done for a typical CMB experiment. Usually you have a pointing matrix P that you apply to the sky, and then that turns into a time stream. So you end up getting a data stream that looks something like this. And then the maximum likelihood map making equation here is essentially a diagonal matrix, or if you include polarization, a block diagonal matrix. And this means that you can essentially treat each pixel independently, or small patches of nearby adjacent pixels. Now with WMAP, it's looking at sort of pixels that are very far away from each other, so you're inherently going to be correlating large fractions of the sky with each other. So whereas before you were able to do this sort of pixel by pixel map making solution, here the map making equation involves inverting this large non-diagonal matrix, and we end up needing to do this with a iterative solution, the conjugate gradient method. And so this is a pretty hefty chunk of the TOD processing, but otherwise everything else is untouched and lower weight than with the Planck LFI. I talked a little bit about the data volume before. This is what I've plotted here is a sample of the raw time order data. And as you can see, it's incredibly discretized. The data are actually reported as integers, which is highly compressible. Just to give a sense, the full data volume for WMAP was 626 gigabytes. And when you compress it, it's reduced to 188 gigabytes. And so this compressed data set, this is obviously going to be part of the eventual data release when we published sort of the beyond, quote unquote, beyond WMAP data, so that it will be relatively simple to reproduce the results that we have here. I also mentioned before that we're not necessarily using the same pipeline as WMAP. We're rewriting it, but doing a lot of the similar things. So for example, there's going to be differences, like the correlated noise model. WMAP had a sort of correlated noise fit for every 1 year of data, whereas we're currently fitting 1/f noise parameters once per week. The baseline estimation is a little bit different. Again, Commander deals with it in 1/f noise, the 1/f sampling, correlated noise sampling that is, and WMAP sort of has a cubic polynomial that they subtract to the baseline. The imbalance sampling, we do a proper Gibbs sampling for this, whereas these parameters were estimated sort of once per scan for WMAP and then averaged. The calibration method, I think, is sort of the only fundamentally different approach. WMAP had this physical parametric model of the gain that was a function of housekeeping parameters. I think the focal plane array temperature and the receiver box temperature, which are both tracked throughout the experiment, and fit that parametric model to orbital dipole data. And then that data was used to give the gain. So there, in contrast, Commander uses the parametric sky model to calibrate the TODs. So this will actually be a very interesting consistency test once we have sorted out all the WMAP analysis. And then finally, the solar dipole is included in the Commander 3 analysis, whereas WMAP subtracted it in the TOD before doing any map making. Once you actually do the Gibbs sampling, it's very lightweight. It takes about 15 minutes for a single Gibbs sample. About a third of that time goes towards the map making. But so basically, this is on the order of just another Planck LFI band. So it'll be, and when I say of the order, it will be less costly because so far the largest time sink is correlated noise sampling, which has not been optimized at all. So basically, this number of like about 15 minutes per sample will decrease, and it'll be very easy to run a Planck LFI plus WMAP K-band for just to start with analysis. So let's look at the actual data fit. So we have a parametric sky model, and you fit the data to it, and we have both, the correlated noise sample, which is very low, and also the parametric sky. So we end up getting a good fit with residuals that look Gaussian. So one of the downsides of this, though, is that if there are going to be any issues, we're not really going to be able to see them in the time stream. It's not going to be quite so obvious. So if there's anything that bears out, we'll probably have to see it in the map making procedure. So I'm just showing here the burn-in procedure for the total gain per scan index, the Ni frequency, 1/f slope, and then also the reduced chi-squared. So this is, again, this is just sort of showing the burn-in, and there's a couple things that are that indicate there's some sort of physical modeling issue. So each scan is about 1 week, so we see these sort of dips in the gain that are about once per year, some kind of fluctuation. And similar FNI, there's some periodicity here that indicates that there's something still off. And one other reason why we believe that we still have an issue is that we can pull out the WMAP gain model, and while our answer is of the same order of magnitude, there are no dips in the WMAP housekeeping based approach. So this is strongly suspecting that we've missed something in the physical modeling. And so when we can actually take a look at the map making. So I've done it for the K-band, and then also just because it's not a big deal to run V-band at the same time, just showing what the V2 looks like. And so this includes the solar dipole and the monopole, which might not look quite so familiar if you're used to looking at WMAP data. So I've subtracted the solar dipole and the monopole, and so the data start to look a little bit better. Now, of course, you can compare this directly to the WMAP result as processed, and you can see that there are clearly some differences, a lot along the ecliptic, for example, and there's something else going on with the K-band, which we'll get to in a little bit. In addition, of course, we have polarization maps. Again, the K-band on the top and the V2 on the bottom. And you can compare this to the WMAP full sky polarization maps. And when you flip between them, again, there seemed to be an issue, some kind of residual in the K-band, but the V-band, it is not as obvious that WMAP is better, although there are some features that I'm used to looking at. But again, the V2 band is actually pretty good. So this is sort of bolstering our hypothesis that it won't be a lot more work to implement the rest of the data sets analysis. So of course, the thing you do at this point is when you take one map and another process, you take the difference, and we end up getting something that looks like this on the left-hand side. This is Commander 3 minus the WMAP solution, and the main culprit, based off of all the things that we've seen, in the WMAP papers, it suggests that this is a side lobe modeling problem. Just to give in comparison, on the right side, this is the Barnes et al. Year 1 analysis, where they propagated what the expected side lobe pickup signal would be over the course of the experiment. And it does look quite similar, although we are open to suggestions. So if people in the audience are familiar with the pattern that I'm showing on the left-hand side, let me know. Co-authorship is on the table. So we did try to take into account the side lobes, and this is what sort of our equivalent of the Barnes et al. Plot. And while the sort of high latitude stuff looks pretty plausible, you can see that there's clearly a near side lobe component missing, especially in the galactic plane. So there's something off with the way that we're modeling the side lobes. And so again, if you are familiar with the WMAP side lobe conventions, let me know, because that means you'll be a co-author and we'll be able to get this analysis out sooner. Now, one sort of interesting thing that came about, though, is when we were trying to do the polarized side lobe correction and got the wrong answer. So what we're flipping between right now are the results of 2 Gibbs samples, one that didn't make any attempt to correct for the side lobes, and another one that quote unquote corrected for the K-band side lobes. And the corrected version introduces these large scale modes along the ecliptic, and you can also see similar sort of structures parallel to the perpendicular to the ecliptic here. Now, this is something that we were looking at as like, well, this looks familiar. And the thing that it reminded us of was the official W-band polarization map. And there were these signals here, these features in the W-band map were kind of a sign that there was an issue with the W-band, and they were not used by the WMAP team for cosmology. So if this is a side lobe problem, that means that we've potentially found a way to improve the W-band polarization map, and potentially we could be bringing the 90 gigahertz from WMAP back into play, which would be really exciting. In addition, we're seeing from Trygve Svalheim's paper, you can look at what the residual of the V-band map is after subtracting the model, and there's a similar sort of feature along the ecliptic here. And so this sort of suggests that maybe there are similar unmodeled side lobes that could be included. So that would be really interesting too, if maybe there's an improvement in the V-band that we could be implementing. So once we're convinced that the side lobes are solved, so that's sort of literally, the latest there. But once we've solved that, and once we're convinced that there aren't any outstanding issues, the next thing that we're hoping to do is solve sort of for the imbalance parameters in addition with the LFI. So I talked about the horn transmission coefficients, essentially that the A and B horns have slightly different gains. And it just so happens that the uncertainty in these parameters, when coupled with the WMAP scan strategy, creates these poorly measured modes, these sort of large scale modes that are projected out of WMAP cosmological analysis. These are modes that the Planck LFI does a really good job at. So in principle, if you analyzed both the Planck and the WMAP data together, these poorly measured modes would be become well-measured modes. And so this is something that we're actually pretty interested in as well, and one of the main reasons why we're excited to run joint Planck WMAP analysis. So we have a homework. First, debug the side lobe model. And once we've done that, we want to analyze all frequency channels together. And this will sort of be our beyond WMAP sort of equivalent analysis. And it'll be really interesting to see if we can actually, fix the W band. Once we do that, we'll obviously need to do a consistency check between the WMAP team's results and the commander output, both in terms of maps and the instrument models. And then once we're convinced that our results agree with WMAP and disagree in ways that make sense, and say disagree in ways that make us look better, we will start to produce WMAP plus LFI Gibbs chains, sort of becoming a Cosmoglobe version 1 data set. And so this is the kind of thing that there's some issues that I brought up, but and this is the kind of thing that we are looking for volunteers for. So if you are interested in this and have expertise, please get in touch with me. I'm very happy to add co-authors on this beyond this final paper for Beyond Planck. So to summarize, it is relatively easy to run a full Bayesian end-to-end WMAP analysis. It takes about 15 minutes per sample per channel, which is on the order of a Planck LFI analysis. I will also say it took a lot less time to write a commander module for this than it did to write the pipeline from scratch. Just again, for a sense of scale, it was about 1,200 lines of Fortran code and commander. I did not know Fortran or commander before starting on this, so it's not an unmanageable task to take an existing pipeline and translate it into the commander code. I said before, the sideload modeling is the main technical problem, but once we're done with that, we're going to be very close to having a true joint LFI plus WMAP analysis up and running. And yeah, to be a bit optimistic, if we figure this out, we'll have a chance of perhaps improving the WMAP analysis. And so that would be very exciting. And so with that, I will say thank you to the European Research Council and Cosmoglobe especially, the grant for supporting this work, and I'll be happy to take any questions.